The normal distribution properties. Last time we have discussed recognizing a normal distribution via its histogram. Um, so once you recognize its properties, you can use it to make statements about probability. And we're going to discuss some of those properties. But first, I'd like to talk about a real life scenario that occurred, and it showed up in the USA Today. And the title of it is When Test Scores Seem to Be Too Good to Believe. And here's a quote about from that article. So Scott Mueller seemed to have an uncanny sense about his students, and how they should prepare for their upcoming state skills tests. Um, the report of possible cheating quickly reached district officials who put Mueller on paid leave. He initially denied any wrongdoing, and ultimately investigators concluded that Mueller had looked at questions for both fifth grade math and science tests in advance of violation of testing rules and then copied them, sometimes word for word, into a school computer. So, I mean, before Scott confessed to this form of cheating, his scores prompted individuals to believe that they were unusual. And so how could they detect that? What kind of statistics would say, hey, this test score really stands out? Um, and this is a very common application in statistics, which is to have detection. And oftentimes you'll see this on Facebook when it makes recommendations for you, or Amazon when it makes recommendations for what you should buy. Okay. So it's using similar types of ideas, different analysis, of course. And in this article on test scores, it's not limited to just Scott. We're going to consider several instances that are discussed in this article in different schools. Okay. So school officials often attribute improvements in scores to inspired teaching curriculum changes tailored to tests or more emphasis on basics such as math and reading. In California suburbs, students jumped from the 17th percentile statewide in second grade to the 85th. So that's a large increase. And similarly, second graders scored in 40th percentile on math, then jumped as third graders to 93rd percentile. Okay, so I need to discuss what is a percentile. And the pth percentile means that the proportion or probability that any individual scores below this value, the percentile, is k%. So in this case, the 93rd percentile means that 93% of school districts scored lower than Montebello, and only 7% scored higher. Okay, and if we're look at the 85th percentile for the third grade, that means that 85% of the scores were less than here than Montebello in 2005. Okay. So one thing that this article talks about is the large increase, but then often when they change teachers, that differential, which will demonstrate that it varies by teacher rather than by a learned skill, goes down. So if there's a large increase and then a large decrease, school individuals have suspect that that individual teacher may have been responsible for that large jump, and too large of a jump is a suspicious outcome. Okay. So one key takeaway so far is I want you to understand what is a percentile. Okay. So if you take a test and you score in the 75th percentile, that means that 75% of all students scored less than you. Okay. Okay. So there's one other thing that they used that helped to indicate how rare an event was besides a percentile, and that's going to be this empirical rule. And so this professor, Thomas at Arizona State, explains this empirical rule and says that a test gain of 3 standard deviations or more for an entire grade are so incredible you have to ask yourself, can this be real? Okay. Or was there some cheating involved? Okay. Um, so this empirical rule is a measure of how many standard deviations above or below the mean did the data fall. And there's some percentiles that correspond to it and probability. So 68% of the data falls within 1 standard deviation of the mean, 95% falls within 2 standard deviations, and nearly all the data, 99.7, lies within 3 standard deviations. And that's 3 standard deviations on either side of the mean. Okay, this next graph is going to show you visually what this empirical rule looks like, but you are going to use this on some of your homework, so please remember this empirical rule. If you prefer to use these pictures depicting it, that's completely fine, and I would expect that. Okay. So 1 standard deviation from the mean, so 1 standard deviation below to 1 standard deviation above lies 68% of the data. So from the average. And note that the average could be the sample average, the population average, or your sigma, which is standard deviation, could be population standard deviation or sample standard deviation. The rule holds for both. Okay. And then 95% of the all data lies within 2 standard deviations of the mean. So the mean, the sample average minus 2 standard deviations to the sample average plus 2 standard deviations. And nearly all the data, 99.7, lies within 3. Please note, I might ask questions like what is the probability an observation lies below the probability an observation is less than the mean minus 2 standard deviations. Well, keep in mind 95% is here, so 5% lies outside this region. So 2.5 here and 2.5 here. Since I'm just asking for the less than, it's 2.5%. Now, this next graph, depending on the question that I'm asking, may be more useful in certain scenarios. And this is a breakdown by region of the probabilities. And probability for a continuous distribution corresponds to the shaded region or the area. So here's the 68% rule. And we're breaking it down here by 34.1% between 1 standard deviation of the mean and another 34% within 1 standard deviation above the mean. And between 1 standard deviation and 2 standard deviations above the mean lies 13.6%. Okay. And here, this is 2.5% of the probability or proportion lies above 2 standard deviations. Again, 2.5 lies below a negative 2. So that being 2.1% plus 0.15% is 2.5%. And this minus 1, minus 2, minus 3, that's the number of standard deviations above or below the mean. So the mean here is represented by 0. This is 1 standard deviation above, 2 standard deviations above, 3 standard deviations above. 1 standard deviation below, 2 standard deviations below, etc. Okay. So that graph is very useful for answering questions about probability. Okay. So the USA Today reported about another school in Central Phoenix on 7th graders at Friendly House Academia. um, which was a charter school. Um, and their scores soared from the 15th percentile in 6th grade to the 92nd percentile in 7th. So that means that they made up 77%. So they increased the performance from going from having only 15% of students scoring better than them to 92% of students scoring less than them. Okay, and that's a difference of 77%. And the principal attributes the gains mainly to the math teacher, who has since been removed from the school. And they said that the teacher had a good understanding of the material and academic standards. Okay. And the principal said that they believe these are legitimate scores, but they didn't hold up when they changed teachers the next year. Okay. The students' mean scale dropped from 586 to 419 in 2010 when they were 8th graders. The percentage who passed the state math test also fell 88% to 43%. Okay. And the gains that they made were 5.77 standard deviations. Not even 3 standard deviations. 5.77. That's a change so rare that it would happen by chance less than 1 in 100 million times. Okay. So one other thing that measures how rare an event is the number of standard deviations that an observation is. And something that calculates that is the z-score. So z-scores measure how far above or below an observation is from the mean. And this is very important. A z-score is going to be the observation x minus the mean, and you divide by your standard deviation. Okay. Now, if we were looking at the empirical rule, the probability z is less than 3 is 99.85%. Okay. And so that corresponds to a percentile of 99.85 if you score 3 standard deviations above the mean. Now, how we get 99.85? We added up 0.15 plus 2.1 plus 13.6 plus 34.1 plus 34.1 plus 13.6 plus 2.1, and then we're at that 3 standard deviations above the mean, and that's what a z-score is. Z-score tells you if you're closer to this, you're closer to this minus 2, or if you're above it, if you have a positive score. And so, as you can see, well, having a z-score of 5.77 standard deviations above the mean is astronomically small. Okay. Now, here's another example. Okay. And IQ scores, in order to understand what they are, it's first essential to understand how an IQ is measured. And different tests have different scoring systems, but the modern system has the average or mean score at the 100 point units, okay, 100 points. And the standard deviation is of 15, so that scores conform to a normal distribution curve. Okay, so they're telling you that in empirical rule that you have a normal distribution curve for IQ scores, and that's how they make the test. So my question is, what range of values corresponds to 95% of all scores? Okay, and we're just going to use the empirical rule. Empirical rule tells you you take the average minus 2 standard deviations and you take the average plus 2 standard deviations. In this example of IQ scores, the average is 100 The standard deviation is 2. So I'm going to go 2 standard deviations below, 100 minus 2 times 15, and 100 plus 2 times 15. So 95% of the scores correspond to have a score of 70 to 130. Okay, so that is the range that it corresponds to. Okay, well, in the empirical rule, I can also find percentile, and I'm asking you to find the 88.85 percentile. And you should notice the 83.85 percentile corresponds to be exactly 1 standard deviation above the mean. So that is, if I was to take 0.15 plus 2.1 plus 13.6 plus 34.1 plus 34.1, that would correspond to exactly this 83.85. Okay. So if I want to obtain 1 standard deviation above the mean, I'm going to take 100 and add 1 standard deviation, 1 times 15. That's 115. So an IQ score of 115 corresponds to the 83.85 percentile, meaning that 83% of all individuals who take this IQ test are going to score 115 or less. Okay. Now, I can also ask you to calculate a probability. I can ask you to calculate the probability someone has an IQ score between 85 and 115. Okay. Well, notice 85, I think that's a certain z-score below. It's only 1 standard deviation below, and 115 is 1 standard deviation above, but we can do the z-score to confirm this. So I take 85, I subtract 100, and I divide by 15. Well, I do that to both sides, and that looks like the probability the z-score is between -1 and 1, and that's 68.3, or 68% according to this. Okay, this one's has a little bit more precise, so this one says 68.3, and I take either of those two answers. Okay. Okay. Okay, so we have 68.3%. I can ask you other questions about probability with IQ scores. I can ask you the probability in individual scores more than 115 on the exam. Okay, so that's 1 standard deviation above the mean. And I can confirm that by taking the z-score. So the z-score says probability someone scores more than 1 standard deviation. Okay. Okay, well, 68% lies between a standard deviation, and so this is how much lies outside, but I only want half because there are two sides to this normal distribution. It's going to be 16.15% approximately. And if I was to add up, well, here's 1 standard deviation right here. If I was to add up 13.6 plus 2.1 plus 0.15, I get approximately 16.5%. Okay. I can do similar calculations. I can calculate the probability in individual scores 130 or more on the exam, but notice 130 is 2 standard deviations, and if I wasn't sure of that, I take the z-score. So x minus 115 is going to be, well, take 130, subtract 100, divide by 15, that's exactly 2. That's 2.5%. How did I get that 2.5%? Well, here's 2 standard deviations. I take 2.1% plus 0.15%. That's exactly 2.5%. Okay. Okay, so, excuse me, 2.25%, not 2.5%. Okay. So one important thing that I'd like you to notice is I can ask you what interval corresponds to probability. I can ask you to calculate probability, but they need to line up perfectly as whole z-scores, like a -1, a +2, a 3. So any number between -3 and +3 you can answer questions about probability with the empirical rule, so long as you have a normal distribution curve. And one thing that you should notice is that larger z-scores correspond to more rare events for greater than probabilities, but the direction of the inequality matters. Larger z-scores with less than probabilities correspond to less likely events. And in the same way, smaller z-scores correspond to more rare events for less than probabilities, but smaller z-scores with greater than probabilities correspond to more likely events. Let's just break down one of these. Larger z-scores correspond to more rare events or greater than probabilities, okay? And so large ones, so let's say it's like 2, it's more rare to have a score greater than 2 is all that's saying. And it's more likely to score less than 2 because you have all these outcomes and all these probabilities. But if I increase the z-score, it gets larger to 3. Well, it's even more rare to have an event that's larger than that, and more common to have a score that's less than it. That's all that's saying. So that's one of the statements. Okay. So here's a real data set, and it's the banking data set with starting salaries by gender. Okay. You can see that the female starting salaries are relatively normal. They're kind of skewed. And the men's starting salaries are very skewed. Okay. If I was to try and guess the average of the female, we know that it lies somewhere close to the peak, but it's not perfectly normally distributed or bell-shaped. And in the males, it's much harder. Okay, you'd have to actually go through the data and add them all up and divide by the number of observations. So here I do that. Okay, so we have our statistics, which is the sample average and the sample standard deviation for males and females. We see that the sample average of females is 5138 versus males is 5956, and the standard deviations are 539 and 690. Okay, so I can go ahead and I can ask some questions like what is more rare, a man whose starting salary is more than 6,000 or a woman? Okay, and here I'm going to go ahead and calculate the z-scores because z-scores tell me how rare things are. So the female z-score is 1.59, and remember it's for larger than, okay? So larger values, larger z-scores are more rare versus a male z-score is 0.6, okay? So it's much more rare to have a woman that makes more than 6,000 than it is for a man. And that's what this z-score tells us. And we can't use the empirical rule exactly for probabilities because they don't lie exactly on the dot of being 1 or 2 z-scores above. Like we can make a statement of a rough approximation, but we can't make an exact one. Later on in this course, we will be able to calculate these probabilities exactly. Okay. Now, what about the assumptions? That's a very important question. If you're doing the empirical rule, you need to know what are the assumptions. Okay. Before we get to that, let's answer one more question using the empirical rule. What's a range of salaries that fits 95% for each group? Okay. Well, all we have to do is take the mean and subtract 2 standard deviations and take the mean and add 2 standard deviations. And we have the mean, we have the standard deviation. So take this number, add twice that number, take this number, subtract twice that number, and do the same for the males. Take this number, add twice this number, take this number, and subtract twice that number. Because that's what the empirical rule says. Okay, and when we do that, we take the mean, we subtract twice its value. Okay, we take the mean for males, we subtract twice it, And this is the interval we get. So we get that 95% of women have a starting salary between 40.60 and 62.16, whereas for men it's 45.76 to 73.36, quite a bit higher. So I asked about assumptions. The assumption that you're making is that your data is relatively bell-shaped and symmetric, okay? So that you have a normal distribution. That's the only assumption we need. We can see, and so when you make your histograms, that is how you're assessing that assumption. So making your histograms is really important. We can see here that for women, this assumption is for women, this assumption is approximately true. It's not a perfect normal distribution, but it's more normal than not. I'm okay with proceeding. For the males, I'm much less okay with that statement. Okay. So here's a rule that works regardless of your data being normally distributed or not. Okay. And that's chebshev. And this says for any data set, regardless of histogram shape, at least 1 minus 1 over k squared of the observations will lie within k standard deviations of the mean. So here's two statements of it. Okay. This statement is with an absolute value, but if we get rid of the absolute value, we get this statement. And this says the average plus k, that should be minus k standard deviations below the standard deviation, and the average plus k standard deviations has probability of at least 1 minus 1 over k squared. Okay, so that is chebshev. Okay, now let's use it for the male starting salaries. What is a range that corresponds to 75% for each group? We use chebshev or the empirical rule, but here we have to use chebshev because we do not have a normal distribution for male starting salaries. Okay, and I'll do it also for females just so that we can see. So we can see that if I take the sample average, I subtract 2 standard deviations, I take the sample average, I add 2 standard deviations, I get 45.76, and 1 over 1 minus k squared, that's 75%. Okay. Yeah. And here's just remarking, you can use the chebshev for the male groups, but it would be more accurate to use the empirical rule for the female group because it is normally distributed or approximately normally distributed. Okay. So that's it for today. Key takeaways are going to be the empirical rule, the chebshev, percentiles, um, and also z-scores. So please remember to remember those concepts. Thank you very much.